Welcome back to the course. And from the past few lectures, we have been looking at multiple tools which helped us to derive the continuity equation and the Euler's equations. And we also looked at the conservation of momentum, conservation of mass, which is in fact uh, a hidden continuity or Euler equation. So where are we currently? Like, which stage are we for solving the whole fluid problem, right? Because at the end, this is nothing but just a mathematical problem. So let's see at what stage are we currently. So talking about the number of knowns which we have. So let me actually choose another color. How about red? Okay. So the knowns and the unknowns. Now, of course, in mathematics, if you have done linear algebra, you have certain sets of equations to solve, and those sets of equation will have a known quantity and an unknown quantity. And depending upon the number of equations and the number of variables which you have, you can solve the equation so that it satisfies all of the equations. So that's a similar thing we are doing here as well. So the known quantities which we have is the density and body forces. Now density, of course, we can calculate it from a physical instrument, right? We can do that. So density is known to us. Body forces, we'll talk about what body forces are. Generally, it's the gravitational forces and the hydrostatic pressure forces which might be acting, right? So those are the body forces. We'll talk about them in a later video, right? And what are the equations which we have till now? So we have the continuity equation, which is one single equation about the continuity of the whole mass. And then we have the Euler's equation, which are three equations. Of course, we derived only one equation, but if you remember, it was from the ith momentum, like the ith momentum per unit mass. So that ith here is 1, 2, 3, which is the x, y, and z direction. So therefore, we have three equations for each direction. So that gives us three equations. So total number of equations which we have is 4. Okay, that's good. But what about the unknowns? Now we don't really know the velocities in the x, y, and z direction. So we have three unknowns in velocity side. But we also do not know about the stresses, because if you remember, we had used these stresses. Okay, this is the Euler's equation which we derived. So of course we had used the stresses here. So we have 6 stresses unknown. In fact, it should be 9, but we have eliminated 3 stresses from symmetry. So just to jug up your mind, if you don't know what, like, we're talking about the stresses. So this is a cube, like it's almost used in tensorial notations. So this is one stress acting on the surface, this is another one, this is another one, and like these 3 arrows you can draw in these 2 surfaces as well, so giving you 9 total directions. But if you solve some mathematical sets of equations, you get that tau 1 2 equals to tau 2 1 and so on, and that really simplifies our math and therefore removes 3 of the stresses from the stress vector. In fact, it would have been, if not, it would have been a 3 by 3 matrix, right? It would have been a 3 by 3 matrix of those stress tensors, giving you total 9 stresses. But from symmetry we took out 6 of them. So we have 6 unknowns here. So how many unknowns do we have? Now we have 6 plus 3, which is 9 unknowns here, and 4 equations. So the order is imbalanced, and which is not good, right? It's not perfectly balanced, and therefore we see here that we do not have a closure in the sense we can't really solve the problem, because the number of equations are less than the unknowns. So a solution would of course be to find more number of equations. And how do we find more number of equations? We look at certain constraints and try and relate maybe the stress and velocity vector, which will give us a few more equations, right? So let's see how do we do that. So moving on to that, let's talk something about the Newtonian fluids. Okay, so this is a crazy term, Newtonian fluids. All right. So what do we have about the Newtonian fluids? So by Pascal's law, if you remember, it was in hydrostatics. So tau I j equals to minus ps del I j. Okay, so this is a pretty fancy notation which I've used here. So this is nothing but the Kronecker delta function. So the Kronecker delta function is 1 if I equals to j, and it's 0 if I is not equal to j. So if I is equal to j, then del I j equals to 1. If not, then del I j equals to 0. So this is the Kronecker delta function. And if we write the stress vector using this notation, we'll get something like this: ps 0 0 0 negative ps 0. Ps is the static pressure, right? If you have let me do that in blue. So if you have water like this, right, so you have water, and you have some height, you can calculate the pressure here, right? P plus rho gh, with P is the atmospheric pressure plus rho gh, which is the density, rho is the density of water, and so on. So that is the static pressure. So again, so I can write this down as like this. Okay, so this is the Pascal's notation, and this is for hydrostatic, which is like normal sitting fluids which are not dynamically moving. And when they are not dynamically moving, we can assume the shear stresses or the other stresses, these non-diagonal stresses, to be 0. So we can do that. But of course, in our case, we are learning about hydrodynamics. So of course, we can't really assume these stress vectors to be 0, and therefore we need to solve it. So considering a fluid, we can say that tau ij is equal to the pressure into del ij, which is the Kronecker delta notation, which we just saw in Pascal's law, plus some other vectors. So these vectors are the non-diagonal vectors. All right. And how do we actually call this? Like, this term is known as the isotropic components on the diagonal of the matrix, which we just saw above. And these are the non-isotropic components. So isotropy generally means that it's continuous and the same on all the sides. So for example, if you choose I and j as these x direction, which is I will be 1 and j will be 1, so it's a continuous pressure, and you can do that with this method, with the water thing which we just saw, static pressure, right? So that is continuous, but you can't really predict the shear stresses which might be acting on the two water molecules. What force are they acting with, right, in different orientations? So we can't really do that. So therefore we are dividing the okay. And one more thing, that I think in the last lecture and previous lectures too, I was pronouncing the word viscous as vicious, which is bad, but anyway, so it's viscous forces, not vicious forces, but anyways. So yeah, this is the non-isotropic components which are on the non-diagonal side, both on and off diagonal sides, right? So this is how we can define our stress tensors. And I'll just copy one experimental graph. Okay, yeah, just a second, I'll just copy the experimental graph here, and here we have it. So of course scientists carried out certain experiments, because who is a scientist without a lab? And we found out that for a Newtonian fluid, the stress vector, or the dynamic stresses, you can call them dynamic stresses because they are acting when two particles are moving against each other or relative to each other, so therefore dynamic stresses. So the dynamic stresses are related to the velocity gradients. So what the scientist saw is that a wide class of Newtonian fluids showed the dynamic stresses are proportional to the rate of strain. Now, if you remember from your applied mechanics class or any other mechanics class where you must have learned about stress and strain, so strain is nothing but how much the material has expanded relative to its original length. So that is the like change in length you can assume it to be. So we saw that the shear stress or the dynamic stresses are proportional to the rate of strain for Newtonian fluids, and for some other kind of fluids that's not the case, but we don't need to focus on these fluids now. We'll just focus on the Newtonian fluids, right? So we got this equation, we got that somehow like tau ij is proportional to the del u I by del xj, or so on, something on. We did some set of mathematical equations which are actually easy to prove, but we aren't going to do that now. And finally we came up with this beautiful equation, tau cap ij equals to mu del ui by del xj plus, now mu is nothing but the viscosity, right? You must have seen this in physics problems involving friction. Okay, so del mu I ui by del xj by del uj by del xi. Okay, so this is something which we got. Here u is nothing but the velocity. Alright, so this is the velocity, and del u I by del xj will give you the rate of change of that particular length in that particular orientation. So that's what we have it. And okay, so let's say this we got an equation which is relating actually now stress and velocity, and that is exactly what we wanted. We wanted more equations. The more equations we have, the unknowns will also increase, because as you can see here we have a pressure variable unknown. Pressure can change, so we have an unknown now, right? So we do have a pressure unknown currently. So let's see what the scenario is now. Let me again simply cut out table which I got, and by the way I'm referring the MIT OpenCourseWare notes. They're really good notes, you should refer them too for a more detailed study. Okay, so yeah, so these are the equations which we have. So let's see what our current status is. We had the continuity equation which gave us one equation, we had the Euler equation which gave us three equations, and now we have the Newtonian fluid symmetrical equations which are giving us six equations. Now how are they giving us six equations? So as you can see here, tau ij I can write, we'll have tau 1 2, tau 1 3, or tau 1 1 of course, tau 1 1, tau 1 2, tau 1 3. Tau 2 1 I'm not writing because tau 2 1 is equal to tau 1 2 if you put it here and see it's mathematically the same thing. So we'll have tau 2 2, we'll have tau 2 3, alright, and then again tau 3 1, tau 3 2 is mathematically the same as this and this, and we'll just have tau t 3. Alright, so we have these six equations here. These are the six equations which we are talking about here. Okay, alright, so now we have totally 10 equations, which is good. Now let's talk about the unknowns. We had three unknowns. Yes, we had three unknowns. We had stresses, six unknowns about stresses. We have that again. We have an add-on unknown, which is the pressure unknown. So that's a gain. But as you can see here, that the number of equations now are equal to the number of unknowns now. So it's perfectly balanced, as all things should be, said by Thanos, of course. But anyways, let's get back. So we do have now a closure currently, and we can really solve the problem. And therefore we'll actually combine. Now this is too messy. We have 10 equations, so that's too much, and 10 unknowns. So let's simplify things a little bit more, so that we get another famously called equation. And so how do we do that? So we had the Euler's equation, and in fact now what I'm going to do is I'm going to switch to the lecture notes, so that we can go through this a little more clearly, because the equations are already written. There you have it. So here we have the lecture notes, which I told before, the MIT OpenCourseWare lecture notes. Okay, so let's see here what we have. So from to form Navier Stokes, now we've not talked about the Navier Stokes, but that is what we're actually deriving. So from Euler's equations, if you remember, we had derived this from the second kinematic transport theorem. All right. So in this equation, for tau ij, I'm substituting tau ij equals to minus p del ij plus tau ij. So I'm substituting that, and through some mathematical steps, I'm getting this equation, which turns out to be 0. This last term turns out to be 0 from continuity. And finally we have this equation, which is a simplified version of Euler's. Not simplified, but like combined. You're combining a lot of equations together to get the Euler's equation, to get the Navier-Stokes equation. Yeah, so this is called the Navier-Stokes equation. So of course it's written here, why am I writing that again? So it's called the Navier-Stokes equation. Let me just highlight that. And yeah, so we are good to go now. And just a new notation here. This is I'm not sure what symbol this is. Maybe we'll call it V for now, or something like that. But it's the kinematic viscosity, because you have different viscosities, and the kinematic viscosity is nothing but the static viscosity divided by the rho. That's the kinematic viscosity. It's just another terminology which we are using. And these are the tensor and vector forms of what we just did. So of course it's notable to note down the Navier-Stokes equation. So I'm going to copy these equations into our notebook. Okay, that's great. We just had the box. Okay. Okay, so I think we'll just leave it at this stage here. All right. So if we actually move down, now we have the continuity equation which was there one, and we have three Navier-Stokes equation each for each direction, because here I can be 1, 2, 3. So we have three Navier-Stokes equations, and the unknowns which we have is pressure and velocities. Now we are considering only the continuity and Navier-Stokes, right? And Navier-Stokes takes care about the stress unknowns which we had. So now we have 4 equations and 4 unknowns. All right, and these are just values of constants given to us, and we don't really care about them. So yeah, I mean, so we just not derived exactly, but we just saw a little part of derivation of the Navier-Stokes theorem, and the continuity equation plus the Navier-Stokes theorems are together called the governing equation. So we have the whole team assembled now. So we have the governing equations here, and alternatively you can also say the continuity plus the momentum equation, which is nothing but the Euler's equation. They together form the Navier-Stokes systems of equations. So this is something just to know about, right? So now we do have a team, really, and in our next class we'll jump into some boundary conditions, because we need to take like the more number of constraints we have, the more number of assumptions we can do, and the more simplify our problem will become. So in our next class we'll talk about some certain boundary conditions, and then on we'll also discuss something about similitude, which is like scaling a big ship into a small model which can be made into a lab, in a small lab, which will act as the huge system itself. So we'll see what all that means in our next lecture. Till then, stay safe and bye bye.